If you are doing it for a slow speed turn, okay, then we do not need any equations to find out the radius of the curve. But for high speed turn, we have an equation to calculate the radius, which you can see over here. Okay, and the question is very simple. They are asking for the radius, the speed is given, super elevation is given, and the coefficient of side friction is given. Okay, can you use this equation to calculate the radius, or is there any problem? Tell me. Any problem? Can you calculate the radius?
It's just balance execution, everything's given.
Yeah. Okay. Any problem? Okay. Now you can see the R is in feet. Okay. And the speed is in miles per hour. Do I need to do any conversion? Okay, the conversion factor is in the equation. Okay. Now if you look at the question, three values are given, right? Speed, super elevation, coefficient of side friction. Okay, three of them are given. I can remove one value and you can still do the question. Which one? This one I can remove and you can still do the question. We can assume. Do we need to assume? The answer is correct. But I don't need to assume because coefficient of side friction comes from this table. And this table has speed. Okay, so speed is given. Even if I don't give you the coefficient of side friction, you will come to the table and find out the value. Clear? Everybody? Clear? Okay. Another question. We have a radius of 800 feet, super elevation is given, and they are asking for the speed. They are asking for the speed. For radius, we have the same equation. Okay. Now, how many unknowns we have in this equation? There are two unknowns, right? Okay. Which ones?
The radius and the.
No, radius is given.
Basically, the speed and the super elevation.
Super elevation. Coefficient of side friction. Okay. Speed and coefficient of side friction. These two values depend upon each other, right? Okay. Clear or not? Sure. Okay. These two values depend upon each other. Okay. I only needed one of them to get the other, but now I don't have any of them, right? Okay. So two unknowns, and both of them depend upon each other. Okay. There are two methods to solve it. If you have two unknowns, I need an extra equation. To solve two unknowns, I need an extra equation. Do we have an extra equation? We don't have. Okay. So what we will do, we will assume one of the unknowns. Okay. We will assume one of the unknowns. So you can see here, for the f value, we have a range given in the table. Okay. You have a range given in the table. Okay. Which value you want to assume? The choice is open. What f should we assume?
We'll assume f and then we'll compare. We found that.
Yes, give me a value. Which value you want to take?
0.17.
0.17? Yes. Fasten. Which value you want to take?
0.15.
15. You 1? 0.10. Okay. So you have this equation. Radius is 800. E is 6%. And you will put your values of f, the ones which you gave me. Okay. Tell me what the speed you are getting. I want the speed at the f values which you have told me. Okay. 0.17, 0.15, 0.10. 13 or 30?
13.6.
13?
Yeah, 13.6.
No conversion, right? You did not do any conversion. And you put supply elevation as 0.06.
Yes.
Okay.
2520.
Ah,
2520.
what world you are calculating this? We already have radius, okay? Yes, 0.1. Ah? What are you guys doing? You are calculating the speed, right?
Yes.
S value.
Yes.
50.2.
51. Now for these four guys, can you change the F value and give the other answers?
52.1.
Huh?
50.2 for the 0.17. 50.2.
You're copying me.
52.5. 52.1.
52.5. Okay, and for this one, 43 point. Okay. When we assumed an F value, we had a matching S value as well, right, in the table? So when you assume the value of F to be 0.15, its matching S value is 45. Did you get 45?
15 is 50.2.
50.2?
17 is 52.5.
50.2, and this is
52.5.
okay. Coming back to the question, when we assume 0.15, the matching value for 15 is 45, right? The speed should be 45. Did I get 45? No. So this value is cancelled. My assumption is wrong. Okay. When I assume 0.17, the matching value for 0.17 is 35. Did I get 35? No. My assumption is wrong. When I assume 0.1, the matching value should be 70. Did I get 70? No. Okay. So in all three cases, my assumption was wrong. But now I have a range for the S value. I know where it should be. Okay, I know where it should be. It should be between these values, right? You can see it's a close range. It's not like one value is 10, the other one is 18. That's why I was saying that 13 is not the correct answer. Okay. Whatever iterations you are making, whatever assumptions you are making, it will always give you value close to the actual value. Okay. So now you can see the actual value is between 40 and 50, right? The actual value is between 40 and 50. You can see I have two values which are very close to 50. Out of the three, two are very close to 50. So let us try 50. Okay. So 50 is here. Okay. So if I put F as 0.14, how much will be my coefficient? Okay. For 0.14, the matching was 50 and I am very close to 50. Okay. Like I cannot make any other assumption now. Okay. I cannot make any other assumption. Because if I assume 0.15, then I am assuming that should be 45. Okay. And it's not close to 45, it is close to 50. Got my point? Okay. So we can stop the assumptions, we can break the trials. Okay. This is my final answer. Okay. Because I cannot make any other assumption now. I am already very close to the matching value. Okay. There is no other possibility to make the assumption. For 0.15, 0.17, 0.1, I had the other possibilities, right? But now there is no other possibility. There is no other value between the matching value and the actual value of the equation. What my point? Okay. So we will stop here, but for the sake of safety, wherever we have to use the speed, I will not say 50, I will say 48.9. Okay. We stopped where? F of 0.14, right? Okay. F of 0.14. F of 0.14 has a speed of 50, but the equation gives me 48.9. Okay. So I will stop my assumptions. I will not assume any other F value, but I will keep my speed same as the equation, not the same as the thing. Okay, because the equation is more accurate and the equation is safer as well. Got it? Clear? Okay. Next thing about the vehicle characteristics is the braking distance. Okay. Braking distance is calculated, as you can see, average speed into the time of braking. Okay. Average speed. So braking means you are decelerating, right? Your speed is reducing. Okay. So the distance covered during change in speed equals average speed into the time of changing the speed. So you are going at 50 kilometers per hour. Then you apply the brakes for 5 seconds. In 5 seconds, your speed changed from 50 to 40. Okay. So how much distance you covered? Average of 50 and 40 multiplied by your time. Got it? Clear? We are starting with a easy case where the deceleration is for stopping. Okay. So the deceleration is for stopping. So there is no final speed. Okay, so it was average, right? Okay, average means what? Initial plus final blah blah 2, right? How much is my final? We are stopping, right? So my final is 0. Okay, so this will be what? Okay, initial speed over 2, right? Okay, and how do we calculate time? How do we calculate, if I give you speed, how do we calculate acceleration? What is the relationship between speed and acceleration? Acceleration equals to speed. Yeah.
Multiply by velocity.
Very good. In which school did you take this? Yes. What is the relationship between speed and acceleration? Yes, Einstein. Yes, Mr. Newton. Because you will be making your own laws, right? So I should better give you nice names. If somebody tells me speed upon gravity, I cannot say Faisal said this. Nobody would believe. So I would say, yeah, Apollo said this. Then everybody would. Yes? Time what? A over T. She's saying A over T. I don't know any female scientists. What is the relationship between speed and acceleration? Acceleration equals to speed and
Delta time.
where is delta T?
Speed divided by delta.
Thank God. Okay, yes. The speed upon time. Okay, speed upon time. Okay. In this equation, I need time. Okay, so acceleration is speed upon time. So time is speed upon acceleration. Yeah, same. Obviously. A, F, same. Right? Okay. So S upon 2 is my average speed and S upon A is my time. Okay. So braking distance equals to average speed multiplied by time. Average speed S upon 2 time S upon A. This is why we have this. Clear? Okay. You combine them, you get this. Okay. I want the distance in feet. Speed is in miles per hour. I need the conversion factor. Okay. There. Okay. Now in this equation, I have this A, which is the deceleration rate. Okay. Deceleration depends upon the friction between the tire and the road. Okay. So there's a coefficient for that, F, which we call as skid resistance. Okay. Skid resistance is a coefficient for the friction between the tire and the road. And deceleration depends upon this, right? So F equals A upon G. F equals coefficient of skid resistance is A upon G, where G is a constant, right? G is a constant. Okay. So if F equals to A upon G, then A equals to F into G, right? Clear now? F equals to A upon G. So A equals to G into F. No? A equals to what? Clear? Okay. Now G has a constant, right? G has a constant. Okay. This is the constant value of G in feet per square centimeters. Okay. So I already have a constant here, and then I added the value of G as well. So this is my final factor, including the value of G and the conversion. Okay. Clear? Now I said we took a simple case. This case is simple because my final speed was how much? 0. You are doing it for stopping, right? Okay. But while you are driving, you will decelerate and your final speed may not be 0. Okay. So I have to change this equation for multiple final speeds, not only 0. Okay. Another factor which will affect your braking is the gradient, right? Gradient affects the braking or not? Yes. Okay. So I need to add that into the equation as well. So this is the final equation. You can see the final speed and you can see the gradient. Clear? Okay. This equation is in feet. The speed is in miles per hour. This equation is in meters. The speed is in kilometers per hour. Okay. But the factors are same. Clear? Okay. Now in this equation I have F, right? F was A upon G. F was A upon G, where G is a constant, right? Okay. H2 gives me a value for A as well. H2 gives me a value for A as well. So G is already a constant, and if I get the value of A, then the whole thing is a number, right? How much is this number then? If A is 11.2 and G in 32.2, how much is F? Okay, so what is 11.2? The normal deceleration rate, and this is the gravity. Okay, H2 gives me the value of A in meter per square second as well. Okay, and the gravity in meter per square second is how much? 9.81. So what will be the value of F in meter per square second? 0.248. Why have you given the same value? What happened? Why the same? Feet and meters are same?
Change
No.
the units both.
Yeah, it's a ratio and you are changing the units for both of them, right? So it will cancel out. Okay, yeah? So it's the same value in whatever units you are taking. Okay, the purpose of showing you this diagram is to, I showed something like this in the previous lecture as well. We are talking about braking. Okay, so the braking starts here when you push the brake. Okay, when I asked a question in the first lecture of this topic about the perception reaction time, somebody called me, somebody said that it is the time for braking. No. Okay, braking time does not include perception reaction. Okay, braking time does not include perception reaction. Braking time only includes after the braking. Okay, braking distance only includes what happens after the braking. Okay, perception reaction time is before the braking. You think before braking, right? Okay, your perception reaction is your brain, yeah, right? So this is happening before the braking. Okay, after you push the brake, perception reaction is done. Okay, then we have the braking distance only. Clear? Okay. Okay, we have an accident somewhere. Okay, and they estimated the speed of 20 miles per hour. And the car has hit the abutment of the bridge, meaning the barrier of the bridge. Okay, abutment means the barrier or the wall of the bridge. You know, under the bridge, there is bridge going over there. Okay, and there you are on the ground, and there is the wall of the bridge. Okay, so that wall is the abutment. Okay, so the car hit the abutment of the bridge. Okay, what was the speed of the car at the time of hitting the abutment? 20 miles per hour. Okay, the car was at a speed of 20 miles per hour when it hit the bridge. How do they know this? Because they have some model which they call as the damage model or the loss model. Looking at the loss or the damage of the car, they can estimate the speed. Okay, and it's actually from the manufacturers. Okay, they test these things that if a car hits something at this speed, what will be the damage? Okay, you may have seen those videos as well. A wall and Toyota is hitting, GMC is hitting. Okay, so much fun. People flying over there.
It's very smart to watch. I mean the simulation and the actual real.
Now you're seeing this. Okay. Need to keep an eye on it. Okay. Thanks. So the speed at the crash is here. Okay, the speed of the crash is here. Is this my initial value or the final value? Final. Okay, final speed is here. When they looked at the road, they found some skid marks. Okay, you know the marks that tires make on the road. Okay, the black marks. Okay, so these marks indicate what? The driver was doing what? Braking. Okay, so if I can look at the marks and I can measure it, I know for how long the driver was braking, right? The marks are for braking. So if I measure the distance, this is my braking distance. Clear? So they measured the distance, okay, and they found that this is the crash and the marks start from here. And from here to here, 100 feet here and 75 feet here. What is here and here? What is here and there? Is the pavement and the shoulder. Okay, pavement is the American term for the road. Okay, people from UK, pavement is the side of the road. Here, this is an American book. So pavement means the road. Okay, so they found 100 feet marks on the pavement, the road, and they found 75 feet on the shoulder. Okay, now all of this is braking, right? This 100 feet is braking, the 75 is also braking. Okay. We can combine them. Total braking 175.75. Okay. But we will not combine them because of the difference in surfaces. Okay. Normally the road and the shoulder are the same surface. Okay. But in this case, the road and the shoulder are of different types. When they are of different types, their friction with the tire will be different. Okay. So that's why you see the two F values are there. Clear? Okay. So I have to calculate, or I have to solve this example in two parts. Okay. Let us move on with that. So this is the first part. The braking distance for the shoulder. The braking distance for the shoulder is 75 feet. Why I started from the shoulder? Because the car hit the abutment after the shoulder, right? And the speed of hitting the abutment is given. So I already have the speed for the abutment, the shoulder, end of the shoulder. Okay. So this becomes my final speed for the shoulder. Okay, clear? And yeah, this is the F factor. There was no gradient. So gradient is gone. Okay. How much is the initial speed here? Okay, any problem? This is the speed where? Here. 20 was here at the abutment. 31 is here. Now how much is the speed here? You know the distance, right? Distance is 100 feet. Okay, and the F value is 0.35. Okay, so how much will be the speed? So you will replace the distance with 100, distance of the pavement, and the F value for the pavement is 0.35. Okay, and this 31 will become my final value. Clear or not? Sorry?
Which one was 13 or 0.25?
Both. No, 0.35. Yes. Clear? Okay. So going back to the question, 20 miles per hour speed was given at the end of the shoulder. Okay, and they measured the distance from the shoulder to the pavement. It was 75 feet. The friction factor for shoulder was 0.25. So I use this data to calculate the initial for the shoulder. Okay, before the shoulder it is pavement. So this becomes the final for the pavement. Okay, so 31 becomes the final for the pavement. Distance is 100 feet. F factor is 0.235, and you calculate the initial for the pavement. Clear? Everything good? Need coffee, right? Bring it. Yes, I need. Okay. Any questions? Okay. Did I miss something? No. I mentioned earlier that braking does not involve the perception reaction distance. Okay, braking does not involve perception reaction distance. Okay, but the total distance needed for stopping needs some perception reaction distance and also need the braking distance, right? You look at something, then you decide what to do, and then you apply the brake, and then the car will stop, right? So it starts with perception reaction, and then the braking will happen, right? So the total stopping distance can be calculated using this equation. This part is for braking, you already used it, and this part is for perception reaction. Okay? What is this part? Speed into time. Okay, you looked at something, signal maybe. Okay, now you are thinking what to do. Okay, so until you do something, your speed is same, right? Okay, so if you take 2 seconds to think, you will keep on moving at same speed for 2 seconds, right? Okay, so that's like this. And what is this 1.47? Conversion factor. Okay, whatever we don't know is conversion factor. Okay, so the first equation will give you in feet, the second equation will give you in meters. First equation, speed is miles per hour, second equation, speed is kilometers per hour. Clear? Any questions? Okay, we have a truck which is coming around the curve. Sorry, not a truck, a driver. Okay, a driver, and he is coming around the curve, so he is running very fast, 65 miles per hour. See, this is a driver. Okay, not a car. So he is running at 65 miles per hour. Superman. Okay. Clear? Without the dog. And when he comes around the curve, he looks at a truck which is turned on the road, and the point from which he looks at the truck, his distance is 350 feet. Okay, the point at which he looks at the truck, his distance is 350 feet. After thinking that he needs to stop, he decelerates at a rate of 10 feet per square seconds. Okay, his deceleration rate is 10 feet per square seconds. At what speed he will hit the truck? Okay, at what speed he will hit the truck? Okay, so we are going to use this equation. So which speed they are asking for? Final speed. Okay, and I need to change one more value in the equation, which is which one? There's a value in the equation I need to change. Which one? Yes, Ali. Yeah.
We don't have gradient.
We don't have gradient. Okay, I will just ignore it. But there's a value in the equation I need to change. It's already in the equation. I need to change.
The acceleration.
Where is the acceleration?
0.348.
0.348 was calculated for deceleration rate of h2. Okay, which was 11.2. Is his deceleration rate 11.2? No, right? Okay, so we need to change it. So first of all, I will recalculate my f value. It was A upon G, A is 10, G is 32.2. How much is that? Okay. Then, what is my final speed? You have everything now. You will not use 0.348, you will use 0.31. Okay, so what is my final speed? The perception reaction time for normal braking is 2.5. 56. Yes.
That's 0.348 to
0.31. Okay. Because 0.348 was calculated in the same way, but it was 11.2. Okay, according to H. Clear? Okay. Now we come towards road characteristics. A very important road characteristic is side distance. Okay, one of the most important road characteristic is side distance. Okay, visibility. Okay, if you do not have enough visibility on the road, then it is not safe. And to make it safe, we can change everything else. Safety comes first, right? Safety comes first. Okay. So we may change the speed, we may change the gradient, we may change whatever. Okay. But we have to maintain visibility. Okay. A stopping distance is a minimum standard of visibility at all locations. A stopping distance is a minimum standard for visibility at all locations. Okay. So it has at any point on the highway, your side distance is not equal to stopping distance. Stopping distance required by the vehicle. Okay. If at any point on the highway, the side distance which the driver has is not equal to the distance he requires to stop, it is considered unsafe. Okay. Clear? For example, if you are designing a freeway with a speed of 70 miles per hour, okay, you will use this equation to calculate how much distance the driver needs to stop. Okay, and since we are doing the design, you can keep the value as it is. 0.34 that can be there. Okay, and the perception reaction time is 2.5. Finally, the speed will be how much? 0, because we are talking about stopping, right? Okay, so this equation will tell you how much visibility should be maintained on this highway. Clear? Any questions? Okay. This is okay just to highlight your interest in football. The General Director of Traffic has put this in their booklet. Okay. So they are telling you when you are driving, it's feel like you are on the football field. Okay. And for God's sake, look at the field. Okay, this is what they are showing, basically. So not looking at the field, there will be a goal, and you will be the goal. Okay, you will become the goal. You will cross the field. Okay, this is what they are showing you. If you are going at a speed of so and so, you can cross the whole field in so many seconds. This is what they are showing. Okay, I think there's 2 seconds or something. Okay, if you are going at a speed of 100 kilometers per hour, you will cross the whole field in 2-3 seconds, something like this. Okay, so anyways, nothing to bother about for me. I will have 2 students next week, no problem. Right? Okay, a driver must slow down to go from 60 to 40 miles per hour on a sharp curve. I mentioned that visibility is the most important standard. Right? So if visibility is not enough, then we can even reduce the speed, which you see over here. They have the road. On the road, the speed was 60. On this road, they had to design a curve, but on this curve, the side distance was not enough. So they reduce the speed from 60 to 40. Okay. They are saying that they want to place a warning sign for the driver so that he can reduce the speed. Okay. If he goes at the speed of 60 miles per hour, there is not enough side distance for him. It will be dangerous. Okay. Now you have seen the traffic signs, right? The size of the sign is standard, right? The height is standard. If it's a circle, then the diameter is standard. Okay, everything is standard. Okay. So for these standard sizes, you can know from how much distance it is visible to the driver for standard sizes. Okay. So this is how they come up with the standard. Right? Okay. So they found that a standard warning sign is visible to the driver from a distance of 120 feet. A standard warning sign is visible to the driver from a distance of 120 feet. Okay. They want to know where should they put the sign on the road. Okay? They want to know what? Where they put the sign on the road. Yeah. Now driver has to do what? He has to go from 60 to 40, right? So how much distance he needs to go from 60 to 40? Tell me. Yes. Distance. You will use as to recommended values. It's a design problem. So 0.348 as it is. Reaction time 2.5 seconds.
412. 412.
412. Okay. So this is the distance to go from 60 to 40, right? He is 60 where? On the road? On the straight road, right? Okay. So on the straight road, he is 60. On the curve, he is supposed to go 40. Now where should I put the sign? Here? No? On the next board? Before? Here? Between 60 and 40. Okay. Now they have given me a value of 120, right? They have given me a distance of 120. Okay? This is distance between what and what?
Between 60 and 40.
Between 60 and 40, you have a distance of 412 feet. Remember? Between 60 and 40, you have a distance of 412 feet. Okay? Now, this 120 is from where to where?
Between the warning sign.
Between the sign and the driver. Okay? Between the sign and the driver. Can you give me this distance?
292.
Okay? He has to go from 60 to 40. He will look at the sign from 120 feet and start decreasing. And the total distance he needs is 412 feet. Okay? So the sign must be how much? 292 feet before the curve. So then when he sees it at from 120 feet, he has enough distance to go to 40. Okay? Clear? Any questions? Clear? Okay. I told you that stopping is minimum criteria of visibility, right? To have sight distance equal to stopping is minimum criteria of visibility. But there are locations in which minimum criteria does not work. Okay? So one of those locations is where the scenario for the driver is complicated. If the road situation is complicated, then the sight distance equal to simple stopping will not work. Okay. What are those situations? Some examples are given here. Okay. The first example here is if you have any crossings. There is an intersection, other vehicles are crossing you, pedestrians are crossing you, or there is a ramp, so people are coming from the side or they are going towards the ramp. So the situation becomes more complicated, right? If you are going straight, it's no problem. Okay, but when they are crossing, it becomes more complicated. Changes in the road itself. Okay, number of lanes are changing, the median is changing, okay, the ramps are changing, something is changing on the road. Okay, and the last one is, these are just examples to give you an idea what is a complicated situation. Okay. But as an engineer, wherever you feel the situation is complicated, it's your decision. Okay, it's your judgment. Okay, the third example is if you have too many distractions around you. Okay, you are driving on the road there are too many things around you. They call it visual noise. Okay, they call it what? Visual noise. Okay, so So you have, what are distractions? You have buildings, okay, you have other cars, you have pedestrians, you have boards, okay, traffic signs, signals, okay. So one or two signs, no problem. If there are many, especially you see if you go to the commercial areas, okay, you will see all these things around you. There are buildings and crossings and signs and markings, everything is there at the same time, okay. So whenever you have a complicated situation, the driver will need more time to think. Okay? Just like the exam. Agreed? The question is very difficult, we need more time. Why? Because we want to think more. We believe that if we think more, Allah will send something in our brains. We did not study for the last 2 months, but now if we think for 15 minutes more, something will come, right? This is belief, right? Iman. So, but anyways, you get the point. Okay? Situation is more complicated, driver will need more time to think. To give him more time to think, I need to give him more visibility. Okay? So he can see this thing in more advance and he will have extra time to think. Got it? There? Okay. Now, the last point, which is related to what we've already done. Now, this is the equation for doing what? D was what? What was D? No, not the value. What is D? Distance for stopping, right? Distance for stopping. Okay. Let's say you have a complicated situation, and I want to calculate how much distance you need to stop. Should I change my equation? Should I change my equation?
Reaction time, maybe.
Yes, but the equation will remain the same because the equation comes from physics, right? You have a moving body, it is going at so and so speed, it needs this much time, so equation will not change, right? Okay, keep it in your mind, don't change the equation for your own sake. Okay, otherwise some of you may get Newton or Einstein in your dreams. Why we change our equation? So equation doesn't change. Okay, what will change? Say again. Reaction time. Okay, so I will use the same equation for stopping in a complicated situation with more reaction time. Okay, and whenever you have complicated situation, your standard will go from stopping distance to decision distance. Okay, in complicated situations, our standard of visibility go from stopping side distance to decision side distance. Clear? Got it? Any questions? Okay, and now you understand why we call it decision side distance, because the driver is taking more time to decide. Okay, everything else is same. So next time we will be talking about another case for decision side distance.